Hello and welcome to Algebra 2 tutorial. We are again taking a look at mathematical modeling. We're going to do another sort of hypothetical experiment, and we're breaking this analysis, this mathematical modeling, into three pieces. We're going to take a look at the data. We're going to analyze that data by writing an equation, and then we're going to take a special look at analyzing the slope and the domain and range. And once we have our model, we can then make some predictions. So that's sort of our roadmap there. So first, let's take a look at our data. So in class, we did an experiment. We had an air cannon, and the air cannon launched a rocket. And so we pressurized the air cannon by pumping it up, and pressure is measured in pounds per square inch, PSI. And then once we launched this rocket, it went a certain distance. So hypothetically here, we're going to take a look at our rocket. If we put up to 20 psi, it goes 40 feet. If we pump it up to 40 psi, it goes 70 feet. 60 psi, it goes 100. And then 80 psi, 130 feet. So now that we have the data there, we can go ahead and do our first bit of analysis, which is to write an equation. And we use our linear equation here, mx plus b. Now I know to use the linear because if I plot these points, they would make a roughly straight line. Later on in the year, we'll definitely do some that don't make a straight line, and we'll have to make a decision on something else to use for our model. But in this case, it makes a pretty good straight line. So we're going to use our linear model. So first, we need our slope, m. So we pick 2 points. I'd pick the first and the last. And we're going to make that into a straight line. So first we need the slope, so we subtract the y values. On top, 130 minus 40. That's our rise. Over the run, which is 80 minus 20. So we subtract the y's on top, subtract the x's on the bottom. We get 90 over 60. We can reduce that pretty easily. The zeros cross out. 9 and 6, you can divide them both by 3. So you get 3 over 2. So we have our slope. Plug that into our equation so far. 3 halves x plus b. We still have to figure out what the b is. So to do that, we pick a point and plug it in. So let's pick the first one. That looks the easiest. 20 will go in for x, and 40 will go in for y. Don't forget to fill in the rest of the equation. And as you can see, now we only have one variable, the b, and we can solve for that. So a few steps here, the 2 and the 20 sort of cross out a little bit. 20 divided by 2 means we have 10 left over. And then we can multiply the 10 and the 3. That gives us 30 plus b is equal to 40. Subtract the 30, and b is equal to 10. So now we have our full equation here. Y is equal to, our slope is 3 halves, and our y-intercept is 10. Now because we are having a context and a word problem here, it might be good to turn this equation into function notation. So instead of using x and y, we'll use letters that have a little bit more context to them. So our y gets replaced with, I'd say, d for distance. So the distance at some pressure, d at p, is equal to 3 halves times the pressure plus 10. So here we have our function notation, and here we just have a regular equation. Hopefully you can see numerically they are the same, but sometimes we just use this version because it looks a little nicer. Alright, so that starts our analysis, but with this we're going to take a look at something a little bit different in terms of our analysis. We're going to take a look at the slope and the domain a little bit closer and analyze what they mean. So first, our slope. So remember, our equation here is dp is equal to 3/2 times pressure plus 10. So what does the slope right here actually mean? 3/2. So remember, slope is rise over run. So your 3 is your up and down, the rise, and the 2 is the run. All right, well, if 3 is up and down, what does up and down stand for in this problem? Well, that's our y values, and y values stands for distance. So it's 3 feet of distance. And the 2 is our run, our side to side, which is x, which stands for pressure. So pressure is on the bottom. So what that means is, if we increase the pressure by 2, that's like we're going to the side 2, running 2, we will rise 3. So the run is psi, pressure, and the 3 is measured in feet, up and down. So if we raise the pressure by 2, we should go an extra 3 feet. So we can put that into a sentence. If we raise the pressure by 2 psi, we expect, well, if I could spell, we expect the rocket to go an extra 3 feet. Now you could also do that. You can write this slope in a different way. I said we might use that as a decimal. 3/2 is the same as 1.5. Well, what do you do with a slope if it's not a fraction? You would always put a 1 under it. And so it's a slightly simplified version. If we raise the pressure by 1, we expect the rocket to go 1.5 feet farther, which hopefully you can see is the same as this statement here. You could do almost any type of fraction you want. It's all the same. 6/4 is also the same. So if you raise the pressure by 4, you would expect 6 feet extra distance. But oftentimes you do the simplest form, the 3/2 or the 1.5. So that's what the slope actually means there. All right, one more thing we want to take a look at in our analysis is the domain and the range. So what are those? So first, the domain, and then we will do the range. So remember our function here, the distance with respect to pressure is equal to, I'll do the decimal this time, 1.5 p plus, what was it, 10? So the domain are all the x values. Remember, this took the place of x. What x values can we plug in? Well, pressure, you have to put in a positive pressure. I can't have negative pressure in my air cannon. That doesn't quite make much sense. So the pressure must be positive. So I would say P has to be greater than or equal to 0. The range are your y values, which in this case will be the distances. Distance. Now the rocket isn't really going to go backwards, so that means the distance must also be positive in this case. So the distance will be greater than or equal to 0 as well. Now if you really wanted to get fancy here, you could put even more constrictions. The air cannon, you cannot pump it up to an infinite amount of pressure. So to be safe, I usually say the pressure must also be less than about 80 psi is about as far as I'm willing to do this. So that also then restricts our distance. If I'm only allowed to pump it up to 80 psi, if I put in 80 for P, 80 times 1.5 is 120, plus the 10 is 130. That means the distance will be less than or equal to 130 as well. A little fancy there. You don't always have to do that bit because sometimes you don't know what the maximum value is. But for our air cannon, I kind of do. I would not pump it up beyond 80 pounds per square inch. All right. So, just a little bit more about domain and range there. Let's take a look now, the one last thing we have to do, predicting. So now that we have our model, we've analyzed the model a little bit, we can do our predictions. This is very similar to our previous video and previous topics, so I'm hoping these go pretty easily. If you want to fly the rocket 300 feet, what pressure would you need to put it up to? Well, this is a y value, and so it's going to go on the left side of our equation. 300 is equal to, I'll use the fraction. I think that's a little easier actually. 3/2 times the pressure plus 10. And then we just solve that equation for P. So minus 10 to both sides, you get 290 is equal to 3/2 P. Multiply by 2 and then divide by 3. So you can see I took 290, I multiplied by 2, and then I divide it by 3, and we get 193. So theoretically, if you wanted that rocket to fly 300 feet, your pressure would need to be 193.3 pounds per square inch. Now it's very unsafe, so I wouldn't do that, but theoretically that's what you would have to do. Alright, now suppose you want to do something else unsafe, and you want to pump up the cannon to 200 pounds per square inch. How far theoretically would the rocket go? So hopefully you can see that the 200 is an x value, not a y value. So our distance, how far our distance would be at 200 psi, d at 200. So we have 3/2 into x, or p, we're plugging in 200, plus 10. This we can do in our head, I believe. D at 200 is equal to, the 2 and the 200 cross out a little bit. You're left with 100. Times 3 is 300, plus 10 is 310 feet. Which is quite far. Again, it's all theoretical, but we can do predictions like that if we have a model for this experiment. All right. So what we've done so far is we've taken some linear data, made an equation, a model for it. We've analyzed the slope and the domain and range, and then we've also been able to use that model to make predictions for experiments that we can't actually do because they would be unsafe. So what I want you to do now is try one of your own here. It's a slightly different scenario, but it's all the same type of math. Good luck.